All right, hi everybody. Thanks a lot for inviting me. And I'm going to talk about kind of object reasoning for the concept of forward manipulation, coming more from this, let's say, applied perspective, like what kind of things do we need to model, or what can we get away with for forward manipulation tasks. And it's going to be actually pretty simple, kind of pick and place tasks typically. And also the goal often of the more recent work is actually not to try to do explicit 3D modeling of things, but operate more or less directly on the point clouds of these objects. So here's an example of the more early work we've done, where you say, imagine you have a kitchen and you have a 3D model of that kitchen, right? Which means you even have models of the drawers and doors, and you have a model of how they are articulated, how they move. In that context, what you can do then is, of course, you can have a system. This is observed with a depth camera. And we also have models of the objects in the scene. So what we then do is we do standard kind of object detection. We match these objects against the point clouds and the color data. And then you can do these kind of nicely controlled manipulation tasks, like you can do planning at a high level, like how do you open the doors and drawers. Okay, how you can then see, okay, where do I pick up an object model? Right, you can do all the higher level planning on top of that. The limitation, of course, of that kind of work is that you assume that you have these 3D models of the objects, which in the real world, in many cases, you do not have. And also, even if you have 3D models of things in the world, then it turns out that going through this bottleneck of 60 pose estimation often results actually in a more brittle system rather than if you would operate directly on the point cloud, because you're kind of abstracting information away. So after this, we moved on and said, okay, let's see, can we manipulate unknown objects? And that means objects for which we have no prior model, or where we're not even aiming at modeling them. So just for context, imagine you have this task where the robot, you can see this is just an external view on the left. On the right side, you can see that's a view from the robot's gripper camera. As a camera that is attached to the gripper. You can see this here on the left picture. And imagine you just want to get that object, like you click on the pixel, or you have a language interface or something like that, pick up the mug. And in order to do this, the robot has to reason about, first of all, what are kind of the objects in the scene, not at a semantic level, but more like, let's say, at the physical level, right? Like a segmentation of the scene into even unknown objects. Then it has a reason about, okay, once I know what the objects are and where they are, I need to be able to reason about how can I pick them up. So what we call graph generation. And then also you want to reason about collisions in the scene, right? Between, for example, the gripper and the object and other objects when you move them around. So the key components for this is really kind of just simple segmentation, graph generation, and collision checking. And we've done a lot of work on training these different components using synthetic data, purely synthetic data. Here's for the scene center generation, for example. You can then, of course, randomize over the scenes, over the background and all these things. And then we had different kind of techniques that we trained on that. It's just a brief summary. I'm not going to go into any details. The most recent one is this object seeker, but many of them are kind of based on contrastive learning ideas, right? Where you say pixels on the same objects should have an embedding that is similar, and otherwise they should be separated. For object seeker, what we did in addition is we also said, if we have multiple scenes and the object appears in multiple scenes, then we want the pixels for that object to be similar in the embedding space, even across different viewpoints and things like that. So that allows you then actually to do kind of object matching and kind of use that to tell the robot which object it should pick up. I'll give you an example for that. Here's just an example what these segmentations then look like. And here again, we're really interested more in the segmentation into objects that the robot can then manipulate. And once we have a segmentation, the next task is, okay, how can we pick up objects? How can we learn to pick up objects? And here the idea is, if you have 3D shape models of objects, you can randomly, let's say, try different ways of grasping them, feed that into a physics simulator, and then kind of shake the object and see for which of the randomly generated graphs the object stays nicely in the gripper and for which one it just flies away, let's say. And you can do this, of course, on GPU. You can do this on parallel. We can do this. This is for 9,000 objects from the ShapeNet database. You can then kind of annotate using this rejection sampling technique. You can annotate all these shapes with graphs that have a high chance of succeeding according to the physics simulation. Okay, so you get kind of positive examples for all these different shapes and objects and how you can pick them up. And then we looked at different ways of kind of learning this. This is one technique. It's called contact grasp net, where you can then train that network to take as input a depth image of the cloud, of the point cloud, the scene, and then it generates here what you see on the right side. It generates kind of for the different points that you observe. For each point, it estimates, would that be a good point for the robot to actually interact with its gripper? And also which 3D orientation the gripper should have in order to interact with that point, okay? So it tries to replicate what we've seen from that physics-based data generation. We try to replicate that in the scene, meaning these are the gripper poses that have a high chance of succeeding, okay? And with that, we can then actually, once we have a point cloud, we can then generate graphs that have a good chance of succeeding. The key trick is, of course, that for the data generation, we needed the full 3D object models. But then for the network training, we train the network on partially occluded point clouds, right? So that's, of course, the key trick here. One other aspect that actually turns out to be relevant is collision checking. Now, you could do collision checking purely kind of point cloud. You have the point cloud of an object, and you have the point cloud of the scene, and then you can do collision checking using voxels or the raw point clouds. The problem is that various aspects of the scene might be occluded. So which means if you just do point cloud comparisons, you're never going to detect those. And rather than going the route of saying we're training a network to do a completion of the scene, we said, let's just train a network that checks for collisions, right? Where again, the idea is more, we're trying to train components that are driven by these tasks rather than first explicitly modeling the scene. So here's the specific network we had is kind of voxelizing the scene in coarse feature voxels. And then we also feed in, for example, the point cloud of an object. And then you can check for an arbitrary transformation. The network is trained to check whether that point cloud of the object is going to cause a collision with the scene if it moves according to that transformation. The nice thing is once the scene is encoded, we can do this very, very fast. So it's actually faster than doing explicit point cloud matching or checking. Okay, and we can do many of those, of course, in parallel. And we can use that also for example, what's called model predictive control, where when you want to try to, for example, figure out how your manipulator can move to a certain position in order, for example, to pick up an object, you need to check for collisions as you're planning the trajectory of the robot. And we can do all of this very, very fast. So now if you go back to that original scene, imagine you say, hey, get me that object, then we can now automatically segment the scene. We can also, for this object, generate graphs using this trained network. And then we use a collision network to figure out which of the graphs are actually reachable without causing collisions with other objects in the scene, right? And then using this technique, first of all, the network figured out that none of the graphs were actually accessible to the robot in that moment. And then here, what you see is the different segments are kind of colored by how much they contribute to these collisions to desirable graphs. And then we can say, oh, for example, the red one here, that is the one that's contributing most. We can now kind of revert the process and say, okay, now let's make that the target of the robot so that the robot can get that out of the way. Okay, so now the robot figures out a graph for that object and picks it up because they were not in collision with other objects, gets it out of the way. And go back to the original scene and now go back to the original task. And now it actually can access the mug. So all of this reasoning is done kind of purely, first of all the components are trained purely in simulation and none of it depends on any kind of object models. It's really operating on the raw point clouds that we might segment, but otherwise it's raw point cloud reasoning. And And another thing you can do now, you could also prompt the system. For example, in the upper left corner, you see a picture of the object that the robot should pick up. So here we have the segmentation model that is also matching these images of the target object against the objects in the scene. And then we get the segmentation and we can pick up kind of target objects. The interesting aspect here is that the target objects, they don't have to be from the same scene. They can be just different things, like here, the Coke can, for example, is also in a totally different position. And the system is pretty robust for matching those against the scene. So rather than training all these components individually through individual networks, we're currently looking at, we have a work under submission where we're trying to do all of that through a single transformer, right? Where the input to the transformer is the scene point cloud, and the output is, on the one hand side, what are the potential graphs in the scene for the different objects? And also, if the input, for example, could be another point cloud of an object, it's going to say, where could you put that object in the scene? Okay. And we're getting, through the single model, we're getting actually better results than through plugging these individual components together. Here you can see an example on the right side, upper left of these videos, where it's picking it up and it's also reasoning about how it has to rotate the object so that it actually fits into the scene. Here's another one. Again, all of it, this is now just through a single transformer. Another line of work was then, if you can now, you have the scene and you can, let's say, segment out the individual objects, then one question is, for example, can you reason about more complex arrangements rather than just picking up an object and placing it somewhere else? So here we had this work, it's called StruCo3D, where the idea is, for example, you have the scene and the task is to put the boxes in a row, like you can see here on the right. And the idea here is, again, we're just training a transformer to reason about these individual object point clouds, segments, in order to achieve this task. Okay, so the high level idea is we first have an object selection network where the input is, for example, language message like, okay, rearrange objects that have the same class as the yellow object into a large circle at the bottom right of the table, something like that. And then we take all the point clouds of the individual objects, and the output of the transformer is then first is to select which of the objects the robot should rearrange in order that are relevant for this task. And then we feed that into another transformer down here that then actually generates a sequence of transformations for these individual objects such that the overall arrangement is achieved. Okay, and this is an autoregressive model because each object placement is based on where the previous objects were placed, so that, for example, you can arrange them in a circle, things like that. Okay, and then the training data we generate different. This is also then in simulation where we generate data for kind of different shapes you might generate, like circles or lines, or setting the table, and then also, for example, kind of different kinds of objects, different materials. In this case, it's as you can see, the colors of the objects is actually still pretty simple, but this can clearly be extended to even more realistic objects. This is what the data set looks like. Okay, all these different arrangements you can generate. And then here's an example. Especially the ones, or the lower ones, are the ones we can generate now, for example, where you just say, put them into a medium-sized circle. And then you can see how the yellow objects are kind of being rearranged. Or you can then generate, for example, lines of objects, right? And you can specify, for example, which objects you're talking about. It's not just grabbing all the objects, but you could say all the blue objects or all the objects are the same color as the fork or something like that. Of course, so far, there's no like general language understanding in there. It's really kind of trained on the data set that we can generate here. But it kind of shows, and here's an example on the real robot, kind of that even with this really low level, simple point cloud reasoning, we can already do things that I think a few years ago, people would typically have said you need really more complex task and motion planning. but you can do many of these things, let's say, in a much more planning-free, heuristic kind of way. So far, everything was kind of fully supervised, right? There was always the point cloud segmentation, the graph poses and things like that. Here in this more recent line of work, we wanted to see, can we do manipulation tasks without actually explicitly reasoning or labeling objects, and focusing much more on kind of the actions that the robot should actually execute. And this, the first line of work was this clipboard. Maybe some of you have seen this, but the idea is it's kind of, it started out with, Andy Zhang did this at Google, transporter networks, where the idea is that you have a top-down manipulation task, and the input to the network is just a top-down view from a camera, and you specify the task where the gripper should go to pick something up and where it should move to place something. Okay, and that turned out to work actually extremely well, even from very few examples, but there was no generalization. It had to be trained, a single additional network had to be trained for every single task. And then, of course, Clip came up. And then what we did with Clipboard is kind of combining these transporter networks with Clip embeddings to get more generalization out of it. And how this works, and for example, this would be if you want to train the network to fold cloth or unfold the cloth. Like here in the left, you give it an overhead view, and then you just tell it in this image, like where the gripper should go to pick it up, this red one here, and then later where it should move it and release the object again. Okay, you just give it very few examples, and it turns out that that works pretty well to kind of then generalize to different orientations and things like that. Let me just give an example here of what you can do, like sweep the beans into the blue zone. Just trained from very few examples. Now, if you'd use the kind of techniques that also we saw here this morning already, I think it's going to be much harder to specify these tasks, right? Because if you have just granular media or stuff or things like that, object-specific representations are just not gonna be well suited for this, right? Sometimes it's much easier to specify tasks without actually reasoning about objects. Here's another example, pick up the cherries and put them in the box. And here the network actually learned to pick up the cherries at the stem, because otherwise you would crush them, because the examples just showed that the pick places were all at the stem. Okay, if you would want to do this in a more object-centric way, then you would first have to have your cherry detectors and then the stem detectors and things like that. And just doing this by demonstration is actually a very convenient way for doing that, I think. So far, this was all kind of top-down. Not perfect, yeah, I know. All top-down kind of manipulation. And now in more recent work, we had this core paper last year, Perceiver Actor, but we wanted to do this in full 3D, which means where the gripper poses can be at any 3D position and 3D orientation in the scene. So here the idea is that the input, it's a transformer, and the input is the language, okay, open the middle drawer, like the task the robot should perform, and a voxelized encoding of the 3D scene. The raw encoding is actually at a 1 cubic centimeter resolution, so very fine-grained. And then we generate tokens for the transformer that have a 5 by 5 cubic resolution. And the output of the transformer is then given the language task and the voxel encoding at a 1 centimeter resolution. It's kind of a classifier over the scene that says how likely is it that that would be the gripper pose that the robot has to move to in order to achieve that task. And the output is then also a discretized 3D orientation over the gripper. Okay, so it's a full kind of 60 pose specification. Let me just give you an example for how that then works. So for example, if this is when it's trained on put the tomatoes in the top bin, then the input to the network is on the right side along with that language command. And then the network again generates target gripper poses, a sequence of target gripper poses that the robot should move to in order to achieve that task. So you can see here the first gripper pose. So it's again XYZ and orientation. Then the robot moves to that gripper pose. And once that happens, we call the network again, now with the new scene on the right. The network output says, okay, the gripper should move down and close. And once it does that, it retrieves it up. And then puts it there. Again, during training, it was not trained. There's no object detector or anything like that involved in there, right? It's just trained on the specific example, like with tomatoes and the top bin. So the definition of what the top bin is mostly given by how the gripper should move in order to get the tomato in there. Okay, so what you see here is just some examples of a single perceiver actor transformer, and it's just trained on 53 demos. So there were a few demos regarding like the hand sand, where it needs to learn that it has to press the top button. Again, if you do this in an object-centric way, you then have to maybe specify where the hose, then put the lime in the bottom bin, tomatoes in top bin. Again, all these tasks trained with a single network from 53 demonstrations, which is in robotics, often we care about not having to do too many demonstrations. But actually where I think this should work, this line of work should kind of move is, rather than training it on 53 demonstrations, which of course doesn't generalize at the compositional level, what happens if you train such a model on 1,000 or 1,000,000 demonstrations, right? Because then you start getting the real benefits of compositional language understanding. All right, one other interesting aspect here was also, if you look at the attention of the network, for example, in this case, the task is turn the right tab, and the attention of the network, if you look on the right side, is on the tab, but it's also putting attention on the top of the faucet. And it turns out the only way to figure out which is the left versus the right tab, you need to look at the context of the whole faucet, right? Because that's how you specify what left and right is. So left and right is not in the coordinate frame, but it's relative to the faucet. And since the faucet can be in any orientation in the scene, the network had to learn that it has to kind of look also at other parts of the faucets in order to detect that. Does that make sense? And the good thing is we didn't have to specify any of this, right? It's just coming through the training data or through these examples. Here's an example now turning the left tab, where it also paid this kind of attention. The problem with this model was, or is that it's computationally pretty complex. So training the perceiver actor on a set of, for example, simulation tasks might take like 2 weeks actually, just because we have these 8,000 voxelized representations for which we always have to generate the tokens, right? And then the transform is actually pretty fast, but all the token generation, everything. So we now recently developed a new work that's called Robotic View Transformer, RVT, where instead of generating explicitly these 3D voxels of the environment, we are, and it's kind of related what Angela also said, we are actually projecting the scene. We're first generating the scene point cloud and then projecting it into different views into the scene. Okay. And then what we do is we run a single transformer that takes as input these different views. And it reasons about, for each image, for example, what would be a good point where the gripper should go in this image. And then we combine the labels from the different images by intersecting them in 3D, and then we're getting the same results that perceiver actor achieved through the voxelized representation. We get that now through the multi-view representation, but the key advantage is that it's way faster to train. So here's just one example on the training curve, where the dashed line is the one we had with perceiver actor. So this is training over 16 days. And with this new representation, we're getting the same quality of results, the same accuracy, 36 times faster only after 1 day. And we can even, by keep on training, we get even better results. Okay, so just again, rather than explicitly going in this voxel space, doing view-based reasoning helps a lot here. While maintaining, of course, the important aspect, I think, is always that we want to maintain kind of the 3D reasoning. I could give one more, but I think I'm just gonna leave it at that then, right? So that we have time for some discussion. Yeah, I think what we see a lot, especially in some of these simulated environments, that people train robots using RL techniques or evaluate their visual pre-training techniques in kind of just 2D, which means, for example, in the simulated environments, if the camera position between training and testing does not move, then it's very easy for these networks to overfit to kind of a reasoning only in the pixel space, right? So I think it's really important to force these systems to reason about the full 3D scene. And I think after the work I've seen here, of course, I would assume that many of you agree with that, right? And how to reason about the 3D scene, of course, there's different techniques: view-based, voxel-based, nerve-based, and that's totally open. I think what's the most appropriate way for doing that. But I think in general, it's really crucial to do that. We've seen that sim2real actually works really well with physics-based simulation nowadays. And this object level reasoning, there's different ways you can get there, right? One is like what I showed in the first part, explicit reasoning, explicit supervision, but you can also get there, for example, by just giving it this action-based supervision that I showed you with this perceiver actor kind of work. And of course, there's many tasks where that is not going to be enough, what I showed you so far, right? If you want to have more fine-grained affordances or reason about more complex things like stuff, things that are highly deformable, liquids, granular media, and all of that, I think then we'll have to think about what is the appropriate representation even for these kind of scenes, especially with respect to how you want to achieve certain manipulation tasks. Yeah, and one question in general is also this kind of notion, this part segmentation, things like that. Should that come out of explicit supervision, or could that just evolve out of kind of in a robotic setting, right? By giving the robot many different tasks, maybe it can just learn to reason about the relevant parts of the objects without you giving the explicit supervision. And with that, I'll thank you.
We have time for one or two quick questions. Yes, okay.
Thank you for this very nice talk. So I like the task, like using language to instruct the robot to do something. So I'm just wondering, like your current framework is always try to train a unified kind of transformer that things. I mean, on the other hand, since we have all those kind of large language model that so why not go the other way? Say we make use of the existing language model to understand language. We use the existing point cloud net to understand the point cloud. Then we just try to connect them together. Why have to go this kind of unified?
Yeah, that's a very good point. So on the one hand side, of course, we are using language models for the language tokens, right? And there's a lot of work going on, of course, where people go from language instructions to kind of a next level representation of the scene or of the task for the robot. We did some work. We just had a paper at ICRA where actually it's called proc prompt, where we use GPT to generate for certain tasks. We actually generate Python code.
I see.
Right, we gave it annotations like through prompting. We told it, okay, these are, and we even were able then to tell it these are the skills that your robot can execute. And then it was able actually to generate a list of Python code that then you can call. The focus of this line of work is a bit more on, okay, even when you have solved that, how do you get your robot to actually do these things, right? And that from a robotics perspective is actually the really, really hard part, right? So that's been the focus here. And so even with this language stuff, like what we did with the perceiver actor or so, these can be used very well to instantiate the language models then. So there's still this higher level that has to come on top. But I agree, yeah, there's a good reason to kind of separate those still out a little bit.
Yeah, thank you. Thank
you. Yeah.
So it's probably a beginner question for robotics. So like when you're designing like graphs, trajectory, we usually focus on collision-free graphs with like trajectories, but that for humans, it's very rare that we would not like glide into other objects and we're graphing something. And is that like, do we care about that in practice? And if so, how do we approach that? Or is it like too far away?
Yeah, that's a great point. That and also was so far still even our work we typically focus on avoid collisions. You don't want to, and especially if you want to do work that's also at some point where industry listens to you, they clearly want to avoid collisions. If you get any collisions, they're going to say, no, we're not going to deploy that on our robot. I think one limitation is still that the robots just don't have the sensing capabilities that we humans have, right? We have this touch sensing all over our body, and robots typically don't have that. So detecting collisions and avoiding them is then not so easy once you are in contact with these objects. But I totally agree, of course, that one way to go is people are looking at learning from demonstrations, so that, for example, the robot generates trajectories based on human demonstrations that might look more natural and things like that. We've done some work on object handover where the human has an object and hands it to the robot, and the robot has to figure out how to grasp it and things like that. There you have to reason actually about collisions with the human fingers, right, and all this kind of stuff. So it gets a bit more tricky. But yeah, I agree. I think ultimately I always say, why are our robots so rigid and stiff, right? Like we should just have a soft skin around the robot so that they can get in touch with things and stuff like that. And there's a whole community out there called soft robotics that actually looks much more at those aspects. He was one. Yeah.
And thanks for the very nice talk and all these nice robotic applications also around this. I have one question actually. You are arguing very much with the direction of starting at point cloud. But in the results you showed, there are all these artifacts, point cloud sensors, also like depth sensors we have currently, they really suffer with photometrically challenging objects like glasses, cutler wheels and stuff. So should we forget about the images and start with point clouds and care about these problems separately?
Yeah, that's a good question. So when I say point clouds, I typically actually mean also kind of together with the vision data, right? And some of that is actually using, like, for example, as I said here with this RVT work, that's exactly the idea of actually projecting it into an image plane, right? So that it is more visual-based reasoning. And then in addition to that, for example, this work only depends on you being able to project the scene into these views. And you could then, for example, rather than just accumulating your point clouds, you could run a nerve model to generate those views, right? It might be typically maybe a bit slower, but that's also the direction we are pushing into, so that that you're not operating really necessarily on the raw data, but on something that's already improved on that. So yeah, I agree. It shouldn't be all just pure raw point clouds. Of course, on the other hand, for many of these tasks, the question is, do you train a model to kind of pre-process and denoisify your data and complete your data? Or do you train your more action-driven part of the model to handle that kind of data, right? Like, as I mentioned, you could do object completion and then do collision checking on the completed objects, or you can just train a collision checker that immediately directly works on the raw point cloud.
Thank you so much.
Thank you.